Welcome back. Unit 2, Lesson 3 coming up. It is about factorials, new vocabulary words for you. Factorials, sigma notation, recursion you've already heard before. But if you look at our lesson objectives today, it's going to be to evaluate and simplify factorial expressions. So that's a new word potentially for some of you. We're going to use summation notation or sigma notation to write sums of sequences and evaluate these sums. So we're going to actually calculate them. And then we're going to talk again about recursive, writing rules recursively, and just exploring that a bit more. But before we jump into some of that, we are going to try the warm-up. I'm going to talk you through it, then I'm going to encourage you to pause and try it on your own, and then unpause and compare your answer with mine. So it says a rubber ball is dropped from a height of 9 feet. So it's up here, it drops 9 feet. It hits the ground and bounces back up 6 feet. So here's the ground right here, bounces back up 6 feet. It continues to bounce, and each bounce it rises 2/3 of the previous height. What is the total distance up and down that the ball travels by the time it comes to rest? So technically, if it's always rising 2/3 of its height, is it ever going to come to rest? So I'm going to leave it at that and let you try to pause and solve it on your own. Then come back when you're done. All right, did you get the answer of 45 feet? If not, you might have gotten 27, you might have gotten 18, but you would be incorrect. So keywords here, we need to find the total distance that it traveled both upward and downward. So if you start with the number 9, right, then you have 9 as your first term, divided by 1 minus 2/3, you get 27. But that would only be one direction. So we need to include the upwards directions. That's only the downwards directions. So if I doubled 27, I need to be careful. I need to go back and subtract 9 because there was no upwards direction here at the beginning, right? So I have to subtract 9 because that included the 9, so it'd just be 45 feet. Another way of doing it is to only start with the 6. So I'm going to start here with the 6 feet, go down, 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 all my downs. So I have 6 divided by 1 minus 2/3, which is 18. Then I double that value to get 36. Then I have to go back and add 9 because it started in that upward and dropped, and that was it. So then I would add the 9 feet to get 45. So regardless, you should have gotten 45 feet. There were 2 different ways to think about it. I've demonstrated them both. If you're still confused, make sure you reach out to your teacher. All right, our new vocabulary words. Factorial. So we have factorial notation. So there's a bunch of information in this little tiny part of the notes right here. It says some important sequences in mathematics involve terms that are defined with special products called factorials. The factorial function is defined as the multiplication of a series of descending natural numbers. So we can see here that 4 factorial, so the explanation point is representing the factorial, and then we need to have only natural numbers, and you stop at the number 1. So if it's 4 factorial, that means we're going to multiply 4 times 3 times 2 times 1 until we get to the 1, then we're done. That's my last natural number, and when I multiply those numbers together, I get 24. 7 factorial just means 7 times 6 times 5 times 4 times 3 times 2 times 1, and if you plug that into your calculator, you would get 5,040. 1 factorial is just 1, and then here, a special case here, 0 factorial is 0 factorial, is 1. So that is a definition, that's something you need to remember. That is a special case. We might talk more about that later when we get into probability. Now what happens if we have n factorial? So n factorial, that means we start with any number, right? Well, we're going to take that number n, and then we're going to multiply it by 1 less than itself, right? So we went from 7 factorial to 6. How do we get to 5? We multiplied 7 minus 2 to get 5 up here. Then I would keep going until I really got to n minus n factorial, which is 0 factorial, which is 1. So you're going to keep going down until you get to the number 1. All right, let's practice. It says write the first 4 terms of the sequence given by a sub n equals 3 to the power of n plus 1 divided by n factorial for n greater than 0. So the first 4 terms, it means we're going to plug in a 1. So a sub 1 equals 3 to the first power plus 1 divided by 1 factorial. Well, hopefully you're just saying that's 4. 4 divided by 1 is 4. A sub 2. That's 3 to the second power plus 1 divided by 2 factorial. That's 9 plus 1 divided by 2 times 1. So 10 divided by 2, so you get 5. A sub 3 is 3 to the third power plus 1 divided by 3 factorial. That's 3 times 3, which is 9 times 3, which is 27 plus 1 divided by 3 times 2 times 1. So it's 28 divided by 6, or if you want to reduce it, you could get 14 thirds. And finally, a sub 4, I'm going to get 3 to the fourth power plus 1 divided by 4 factorial. Well, 3 to the fourth power is 3 squared times 3 squared, which is 9 times 9, which is 81 plus 1 divided by 4 times 3 times 2 times 1. 81 plus 1 is 82. 4 times 3 is 12. 12 times 2 is 24. They are both even, so that would be divisible by 2. So I'm going to get 41 twelfths. And there are my first 4 terms of the sequence defined by this rule right here. Example 2. We're looking at some factorial expressions here, and we need to try to simplify them. We need to try to reduce them to the simplest possible form that we can. So I see some numerical values that have factorials, and then I see some n's, some algebraic expressions that have factorials. So let's go back to we'll deal with both of them. But here we have 4 factorial in the numerator. You can write it all out, 4 times 3 times 2 times 1, and the denominator I have 3 times 2 times 1. And this is all being multiplied together, right? Then I have my n plus 1 factorial. So n plus 1 is a number. Remember, that's a number. That's the first number. Then I'm going to multiply it by 1 less than that. Well, n plus 1 minus 1 is just n. And then I'm going to multiply it by 1 less than that. And I would keep going infinitely, right? So I'm going to have n plus 1 times n minus 1 times n minus 2, etc. Because that's the rule. You go 1 less 4, 3, 2, 1. So it's n plus 1, then n minus 1, etc. Okay, in my denominator, I started with n. So I'm going to have n, and then 1 less than that is n minus 1, and then n minus 2, etc. So remember, all of these numbers, all of these values are representing numbers. N plus 1 is representing a number, and they're all being multiplied together. And when you have all these numbers multiplied together, we can cancel 1 for 1. So the 3's cancel, the 2's cancel, the 1's aren't doing anything, but we'll go ahead and cancel them. The n's cancel, the n minus 1's cancel, etc. So everything from here down cancels. So the only thing I have left in my numerator is 4 times n plus 1. And the only thing I have left in my denominator is just a whole bunch of 1's, right? They're canceling and becoming 1's. So 4 times 1 times 1 times 1 times n plus 1. So you can either write 4 times n plus 1, or you could write 4n plus 4, and those are the same answer. We would accept either one. All right, now be careful on this second one. There is now a plus sign that we snuck in there. So it's no longer just a whole bunch of things multiplied together, right? So if we have n minus 1 factorial, that is, right, so I'm going to take n minus 1 factorial. So it's n minus 1 times n minus 2, etc. So I can just leave it as n minus 1 times n minus 2 factorial, or I can just back it up and leave it as n minus 1 factorial. So I'll explain that in a second. So I'm just going to leave it as n minus 1 factorial. Then I'm going to add, well, this n factorial right here, I'm going to change my colors. That's n times n minus 1, etc. So I'm going to keep going down. So I'm not going to write n minus 1 times n minus 2 times n minus 3, etc., n times n minus 1 times n minus 2, etc. I'm just going to expand it. N factorial is the same as this, and n minus 1 factorial just stays n minus 1 factorial. Well, we have an interesting situation here. If we let a equal n minus 1 factorial, then in our numerator we would have a plus n times a. Right? This would be an a, n minus 1 factorial is an a, n minus 1 factorial is an a, so we'd have a plus n times a, which means we could factor out that a and get 1 plus n. All right, well, let's think about that. My denominator doesn't change. I'm just going to keep it as n plus 1, right? There's nothing to do there. It's just an n plus 1 in my denominator. So over here, I just have an n plus 1 and an n plus 1. Ooh, look what happened right here. My n plus 1s can cancel. So I'm just left with what? I'm left with a. Well, what is a? A is n minus 1 factorial, so technically my answer is n minus 1 factorial. Now, what did I do? Okay, let's backtrack. This n minus 1 factorial and this n minus 1 factorial are the GCF. It's the greatest common factor. I'm factoring out, that was the letter A. I'm factoring that out and I'm putting it in front. So that n minus 1 factorial is in front. When I take that in front, well, I divide n minus 1 factorial divided by n minus 1 factorial, I get a 1. I divide n times n minus 1 factorial divided by n minus 1 factorial to get my plus n right here. And then in my denominator, I have my n plus 1. 1 plus n and n plus 1 are identical, so my answer is just n minus 1 factorial. And that's it. It's a little more complicated though, so check out, that was a factoring technique. If you're not sure, ask your teacher or look for some other example problems to practice. All right, let's try this third example, letter C. So my numerator is n plus 3 times n plus 2 times n plus 1, and I could keep going, factorial, right? So n plus 3 times n plus 2 times n plus 1 factorial. It never stops. My denominator is just a simple quadratic, so I need to factor that simple quadratic. Well, the first number, 2n squared, is a prime, so it's just going to be 2n and n. My 3 is prime, my negative 3, so I have to have a negative 1 and a 3 combination or a negative 3 and a 1 combination. So I'm trying to get a positive 6 here in the middle, or sorry, a positive 5, excuse me, here in the middle. So what do I need to do then? Well, I need to have a positive 6 and a negative 1. So this is my negative 1n, this is my positive 6n to get that positive 5n in the middle. So it's 2n minus 1 times n plus 3. So that factors to give me 2n squared plus 5n minus 3. So now we're going to try to cancel. So n plus 3 cancels with n plus 3. That's the only thing I can cancel. I'm done. So I'm going to regroup, and I'm just going to make this n plus 2 factorial. I'm going to put that back in there, and then I'm going to divide it by 2n minus 1. So this is my final answer. If you had left it as n plus 2 times n plus 1 factorial, that's fine. It's not as simple because moving that n plus 1 back in and making it just n plus 2 factorial is a little bit simpler. And remember, we're trying to simplify, but we'd probably just let you leave it like this as well. Okay, our other vocabulary word, sigma notation. So we have this symbol right here. It's the Greek letter sigma. And in mathematics, it's the summation notation, or you might hear us call the sigma notation, and it means the sum of. So you're taking the sum of a bunch of terms. So how many terms? Well, that depends on our index, where it starts, where it ends, and then we would determine how many terms that we would take the sum of. So I is called the index, right? So if you have I equals 1, then 1 is your lower limit, or it's where you're starting. You could start at any value, but you'll see a lot of them start at 1. And then n up here is called the upper limit, and usually that's a numerical value, and it tells you where you're going to end. So we're taking the first term in this case plus the second term plus the third term, and we would keep adding them together until we get to the nth term. So plugging in 1 to get the first term, plugging in n to get the last term, and seeing how many terms we have in between. So again, the sigma notation means you're taking the sum of a bunch of numbers. So if we look at example 3, it says find the following sum. So your index starts at 3, that's my lower limit, my upper limit is 6. So what we're doing is we're plugging in a 3 for I, so we're getting 1 plus 3 squared. Then we're plugging in a 4 for I, then we're plugging in a 5 for I, then we're plugging in a 6 for I. And then we would actually calculate those values. So 9 plus 1 is 10, 16 plus 1 is 17, 25 plus 1 is 26, 36 plus 1 is 37, and then we would just do some quick math, try to add that together. Sorry, I'm trying to do it in my head real quick. So 27, 53, so I think that's 90. Right, so the sum of those 4 numbers, this is, you could think of this as the third term, the fourth term, the fifth term, and the sixth term, or you could make it the first term, but you're plugging in a 3 to get the first term. But regardless, the sum is equal to 90. So it says create the exact series from part A, however we want our starting index to be I equals 1. So if we're trying to create that same thing, but we start at 1, well, first of all, where do we end? So some people might say, oh, there's 3 terms, 6 minus 3 is 3, but you can see here there aren't 3 terms, there are actually 4. So there's 1 more than whatever the difference is. So we have to go from 1 to 4 because there were 4 terms, the third, the fourth, the fifth, and the sixth. When I plugged in a 3, 4, 5, and 6. So I'm starting at the number 1 because that's what I was asked to do. So I'm shifting this expression, right? So instead of having 1 plus I, that wouldn't work because I need to get a 3 here. So if I'm going from 3 to 1, I'm shifting to the left 2 units. And we know when we shift to the left 2 units, you do the opposite, right? Which is to have a plus 2 inside with the x value, and your index is really representing your x value in this case. So you're going to end up with I plus 2. So now you should have the exact same result. So you would have 1 plus 1 plus 2, the quantity squared, plus 1 plus 1 plus, or sorry, 2 plus 1, the quantity squared, plus 1 plus 3 plus 1, the quantity squared, etc. Oh, sorry, 2 plus 2, 3 plus 2, my bad. Because this is the plus 2, which is staying the same. And then I'm putting in my index. Sorry if I confused you. The 1, then the 2, and then the 3. And then I would have 1 more, plus 1 plus, the index is now at a 4. I'm adding 2 to it. I'm squaring that value. Right? So we end up getting the same thing because this ends up being a 3. This ends up being a 4. This ends up being a 5. And this ends up being a 6. But this is how we would rewrite this sigma notation from above so that I could start with the index of I equal to 1. What did I do? I had to shift this I value to the left 2 units, and I compensated for that here by adjusting my I. All right, here are a few problems that we can practice. I'll take you through number 1, and then, or here, number 4, and then you guys can maybe try number 5. I guess they're slightly different. So let's do example number 4 together. You can also pause and try it on your own. So here I see my index is starting at 1, ending at 200. I'm computing. So what does that mean? Well, again, if I have a sigma notation, that means I'm taking the sum of the first 200 terms. So the sum of the first 200 terms, I'm starting with the first term, ending with the 200th term, so I'm trying to find the sum of the first 200 terms. So let's see, what is the first term? The first term is negative 15 halves times 2/3 to the 1 power. So if I multiply that, I would get a negative 5. A sub 2, negative 15 halves times 2/3 squared. That's negative 15 halves times 4/9. If I cross cancel here, so 3 goes into 9 3 times, goes into 15 5 times. 2 goes into itself once, goes into 4 twice, so I would have negative 10 thirds. You might already see what the pattern is. Is this an arithmetic relationship or a geometric relationship? And if you're not sure, you can do one more term. So I'm going to do negative 15 halves times 2 thirds cubed, so negative 15 halves times 8 over 27. Again, cross canceling. And I would get negative 20 over 9. So what am I doing? Hopefully you see that you are multiplying by 2 thirds. It is a common ratio. So your common ratio is 2 thirds. My first term is negative 5. So I'm going to use the sum of a geometric series. So I'm going to take the sum of the 200 terms. I have my first term times 1 minus my common ratio raised to the 200th power divided by 1 minus 2 thirds. So go ahead and calculate that, see what you get. This is a massive number right here, so what's that approaching? Hopefully you're thinking to yourself that's approaching 0, because any number that's less than 1, common ratio, right? If you didn't do that, you can just plug it into your calculator, but you should have gotten negative 15. All right, number 5. So number 5, it says we're going to calculate n, given that we have the sigma notation from I equals 1 to n. We have this algebraic expression, and we know it's going to equal 731. So what does this mean? It means if we take the sum of the first n terms, starting at the first term through the nth term, we should get a sum of 731. So again, do you know, is this arithmetic or geometric? Hopefully you can look at it and you know if it's arithmetic or geometric. If you don't, then actually plug in the number 1 and calculate it. So we plug in the number 1, we get 5 minus 2, which is 3. Plug in the number 2, we get 10 minus 2, which is 8. Plug in the number 3, we get 15 minus 2 equals 13. And hopefully you can see that we're adding 5 over and over and over again. This is a linear relationship. It's an arithmetic relationship, right? We don't know n. We know our a sub 1 is 3. We know our common difference is 5. We know that the sum of the n terms is 731. So 731 equals n divided by 2, and I'm going to take twice my first term, 2 times 3, plus my common difference times n minus 1. So I'm going to solve all of that. So hopefully you can do this on your own. If not, you can pause, try it on your own, or you can follow along with me. So we're going to get 5n squared plus n minus 1462 equals 0. So that means it is factorable. You could graph this on your calculator to see where it's going to intersect the x-axis. And you should see it's going to intersect at 86/5 or at 17. Because we are talking about terms, can we have a fraction of a term? No, we cannot. We can only have a natural number. So how many terms are there in order to make this work? There are 17 terms. So you should have gotten an answer of 17. So sigma notation, we just discovered, can be used to represent a geometric series, right? The sum of a bunch of numbers that are related geometrically, or a sigma notation could be used to represent an arithmetic series. And now we also have the sum of an infinite geometric series. So it has to converge, which means your absolute value of your common ratio needs to be less than 1. So if we have an index and then it's ending going to infinity, then that just means you're going to add all of these terms together until you get the end. Actually, I shouldn't even have an end point there. You can just put dot plus dot dot dot, right? It's never going to end. So find the following sum. we're starting at our first term when we plug in a 1, and then we're going to go to infinity, which implies that it's geometric, right? So let's check and see. So a sub 1, we're going to plug in the number 1. We get 3/10. A sub 2, we're going to plug in the number 2, so 3 over 10 squared, which is 3 over 100. A sub 3 equals 3 divided by 10 to the third, which equals 3 over 1,000. So hopefully you see there that you are multiplying by 1/10 to get from the first term to the second term, or the second term to the third term. So my common ratio is equal to 1/10. That is less than, the absolute value is less than 1, so I'm going to jump right into my sum of an infinite arithmetic series. My first term is 3/10. I take that divided by 1 minus the common ratio, which is 1/10. So 3/10 divided by 9/10. Oops, I don't know how that changed. 3/10 divided by 9/10 equals 3/9, which is 1/3. So the sum of this series from 1 to infinity is equal to 1/3, and the absolute value of r is less than 1. So we know it works. All right, recursion revisited. We're back with recursion. Recall that a recursive rule for a sequence always gives 2 pieces of information. Number 1, you need to tell us where that rule begins. What's the starting point? What's the starting term? And then we need to know what's happening over and over and over again. How do we get the next terms, the successive terms? Are they adding by a number, subtracting by a number, multiplying by a number, dividing by a number? So that's what we need to know. So it says recursive formula may have more than one starting term depending on the nature of the sequence. So you need to look carefully at the sequence, make sure that your recursive relationship is defining it properly. Here it says, find the value of a sub 5 given that the sequence is a sub 1 starts at 4, and then here is the relationship of the successive terms. So we're trying to find a sub 5. Well, if a sub 1 is 4, a sub 2 is equal to 5 times a sub 1, which is 5 times 4, which is 20. A sub 3 is equal to 5 times a sub 2, which is 5 times 20, which is 100. A sub 4 is equal to 5 times a sub 3. A sub 3 was 100, so we get 500. And finally, a sub 5 is equal to 5 times a sub 4. So that's 5 times 500, which is 2,500. So the fifth term is 2,500. Now some of you might have been like, oh, a sub 1 is 4. All I'm doing is a geometric sequence. I'm multiplying by 5. I would get 20. Then I would get 100. Then I would get 500. And I would get 2,500. So that is exactly what we did. Here's another recursive relationship. We have a rule that says a sub n equals a sub n plus 1 equals a sub n plus 3n minus 1, and our starting point is 8. So the first term is equal to 8. Write the next 4 terms of the sequence. Well, a sub 1 equals 8. A sub 2 equals a sub 1 plus 3 times 1 minus 1. Again, why am I putting a 1 in here for n? Because a sub 2 is actually n plus 1, so I put in a 1 for n. So be careful, right? I'm putting in a 1 for n, a 1 for n. So that's what I should end up with is 8 plus 3. 8 plus 3 minus 1, which is equal to 10. A sub 3 is equal to 2 plus 1. So we're taking a sub 2 plus 3 times 2 minus 1. A sub 2 is 10. 10 plus 6 minus 1 is equal to 15. So a sub 1 equals 8. A sub 2 equals 10. A sub 3 equals 15. Now I need to find a sub 4 and a sub 5. So a sub 4 is a sub 3 plus 1, so I'm taking a sub 3 plus 3 times 3 minus 1, so that's 15 plus 9 minus 1, which is 23. And you might have a pattern you might see over here, so you might get to stop. We just have a plus 2, then a plus 5, then a plus 8. Oh, look at this. This is plus 3, this is plus 3, So you might be thinking, oh, that's probably a plus 3 again, which means it would be plus 11, and I'm guessing my fifth term would be 34. Let's check. A sub 4 plus 1 equals a sub 4 plus 3 times 4 minus 1, which is, oops, I forgot to put that here, 23 plus 12 minus 1, which is indeed 34. So here are my first four terms. Notice, this is going to come back in our next lesson, the second difference was common. And how does that relate to this part here? All right, moving on. Our last one. Oh, maybe that was, yep. Last one here, write a recursive rule for the sequence. So this is called the Fibonacci sequence. Fibonacci starts with 1, and then it goes to 1, then 2, 3, 5, 8, 13, 21. What do you notice is happening? Well, a sub 1 is equal to 1. And how are we getting a sub 2? Don't really know. A sub 2 is also equal to 1. How are we getting a sub 3? Well, if you add 1 plus 1, you get to 2. If you add 1 plus 2, you get to 3. If you add 2 plus 3, you get to 5. 3 plus 5, you get to 8. 5 plus 8, you get to 13, etc. So how do I represent that using recursive rules? So this time, because you're adding the previous two to get the next one, you need to define the first two terms. So a sub 1 equals 1, a sub 2 equals 1. So now I'm trying to find a sub 3. So a sub n plus 2, right, if I plug in a 1 right here, because my domain is usually the natural numbers, I plug in a 1, I have to take the two terms before it. So if I plug in a 1, I have to take the second term and the first term, so that's one way, and this is when n is an element of the natural numbers starting at 1. This recursive rule would work. If you want to make a recursive rule where you're plugging in the number 3, like say, hey, I want to get the actual term, so if I plug in a 3, I want to get the third term. So then you would have to take the first term and add it to the second term, right? If I plug in a 3, this is for n as natural numbers, except n is not going to equal 1 or 2. So we're going to start with the number 3 here, right? So you're starting with the number 3. Plug in a 3, plug in a 3, plug in a 3. We get the first term plus the second term equals the third term. Great. Could I represent this relationship any other way? Sure. I could say a sub n plus 1. If I'm going to make this a sub n plus 1, then what am I going to plug in for n to get me started? Well, if I have the first two terms given to me, so I want to find the third term. So this would be when n is an element of the natural numbers, except I'm starting with the number 1, or sorry, the number 2, excuse me, I'm excluding the value of 1. So I'd put in a 2 here. Here is starting with the number 3. Here is starting with the number 1. For this relationship, for this relationship, for this relationship. So I could have a sub n plus a sub n minus 1. So think about it. I kind of went through that really fast. I'm sorry. It's hard to explain all this on a video and you can't ask questions. But there are 3 different ways that you could use to write this recursive rule. There's actually even more, but we would start there. And you always have to identify how you're starting that pattern. This is the one I would demonstrate in class because we've made our domain the natural numbers, but if you wanted to find the third term by plugging in a 3, you might want to have this, but then your domain changes, right? So just be aware of that. And then this one kind of is just an option, doesn't make a lot of sense. Anyway, that's it from me. See you later.